If you want to speak in English, feel free to speak in English. I think it's an international conference, so it's better to speak in English than in French. So I don't find a point to call it international if we are speaking in French.
De toute façon, je tiens à remercier à tous en français et dire les premiers mots en français, mais de toute façon, j'ai plus l'habitude de parler à maths en français, donc je vais changer en anglais. So, the topic that I'm going to talk about is some asymptotics for sums of random variables, as you can see. I will start with something really very classical and then try to get an overview of asymptotic results, basically getting interested on almost sure convergence and some variance of the results. So I will start for something really very classic, and then go to some more recent topics, and have a final word on some consequences on the statistical side of this problem. So the introduction and the statement of the problem is really very classical. So it says about 100 years old, and so you seek for a strong law of large numbers. So you get a sequence of random variables, and you seek to change or to find, normalizing constants that allow you to stabilize be recognizing as something which is basically well known. Of course, so the
Okay, so apparently I need a new microphone. I will go into the discussion about something on dependence and so on, and say a few words about some recent tendencies on the literature on this kind of problems. So I will basically be interested on almost sure convergence. But of course, as you know, and is well known in the literature, you can also look at other modes of convergence. So I mentioned here the central limit theorems with convergence and distribution. But of course, you can be interested on LP convergence and a few other variants of that. But I will only talk about almost sure convergence today. Now, the most well-known result is the Kolmogorov strong law of large numbers, which dates back to 1933, where you have, you just identify the normalizing constants that allow you to get some convergence. Of course, I'm just stating here with the mean value, but throughout the talk I will basically be assuming that the mean value is 0, so just to make simple statements a little bit simpler. Now, we will be playing about with the normalizing term over here. So looking at different ways of normalizing this summation and how this reflects into the convergence rates and so on. Now, a few words about something really very simple, which you all know, is how we prove this kind of results. So basically, we look at this term, along a convenient subsequence. You have this simple upper bound. This is really very simple. And you just argue that this summation here is convergent, and then you just try to control whatever is happening in the remaining terms. So, this is when you have variances. Now, the main point over here, of course, the main point of this proof is this numerator that you have here on this term says n squared terms. I'm assuming IID, of course. So this term here behaves as 1 over n squared, and so you know it is convergent. So the main argument about this proof is you are trying to stabilize variances. Okay? So this is something that I want to point out because this has an impact on something I will mention later about when you start discussing dependent random variables. Now, of course, this is the proof when you have variances. When you don't have variances, you just need a little bit of extra effort, but you use truncation and some kind of some variant of dominated convergence to get the same control without these kind of upper bounds. But truncation helps you, of course, in order to get the random variables, the control of the variances. Sorry. Now, as I pointed, the main point about these kind of proofs, and this will be more or less present on all the proofs that allow you to get some kind of almost sure convergence in this setting, is that you try to stabilize the variance of partial sums. Once you have control on the variance of the partial sums, you basically, well, of course there will be technicalities to solve, but you basically get a good control on what is happening. So much of it goes on with variance of partial sums. Now, independence can be relaxed, and it took a couple of years. Identically distributed, but then you have to be a little bit more careful about the growth rate of the variances. And moreover, you don't even need pairwise independence. You can go a little bit further, and you just can assume that the pairwise covariances are negative. Well, this has a connection with something that I will mention later on, and which is very trendy nowadays, where people started to be interested on concepts or variants of concepts of negative dependence between random variables. So here, the thing is that you have covariances which are negative, so the terms that come up on this numerator over here that add a few extra terms beyond the n squared terms that you have in the independent case become negative, so it helps stabilizing the variances. So again, I'm stressing on the stabilization of the variances. Now, this kind of argument, and well, here, of course, we are going along a convenient subsequence. Well, this is not the only choice, of course, but the idea is that you go along. Do exist, okay? Now, you can prove, and this was proven again by Marcinkiewicz and Zygmunt independently. Well, again, with different tricks, with different approach, but most of the argument was based on truncation and variance stabilization of what is happening. And so you have the equivalence between this convergence here and the existence of the p-th order moment, where you assume p to be strictly smaller than 2. Well, actually, larger or equal than 2 basically is not interesting because we all know that at least in the IID case we have the central limit theorem. So if you have variances, once you have the central limit theorem, not much is really left to be to get interested on this kind of stabilization. Well, I'm not going into details, but you can have some information about the constant C that you have over there. But basically, we will taking it to be 0 because, as I mentioned, I will basically be assuming that the random variables are centered. So you can always assume that this is 0. Well. In fact, a few years later, again, with a different method to get moment control, this author proved that this equivalence over here is actually equivalent to the LP convergence. Okay, so again, instead of looking at variances, you just look at the different order moments, and then you get the same kind of approach. So the basic idea is stabilize whatever moments that you are interested in. Now, here we might or not, depending on the value of P, have variances. Have expectations. That the expected value might exist for these random variables. It is relatively recent that you can go without any assumption. You can prove this kind of proof, this kind of convergence without any assumption on the existence of moments, as long as you don't get interested on the summation of the random variables themselves, but you do some kind of centering with convenient truncation. Of course, now the normalizing constant over here, so the Bn that appears over there, well, notice that this assumption here is implying these two sets of assumptions, and how the almost sure convergence rewrite is like this, and then so you are linking the normalizing constant, so the one that gives you some information about the convergence rate, with the truncation sequence that you are using. Notice that there is no assumption about moments, but of course, as you are dealing with truncated random variables over here, so you ensure that these moments do exist, and then you can have some control about what is happening over here. Now, there are some restrictions about the normalizing sequence Bn, so it should grow faster than n itself. And then you have this kind of convergence with sufficiently fast normalizing constants. Now a few extras. So if you don't want to have a normal a truncated centering terms, then you have to assume that Bn goes to infinity, Bn over n goes to infinity. This is not only increasing, but it should be really increasing to plus infinity. And then you still have this kind of convergence over here, regardless of the existence of moments of the random variable. So they are still IID, but you don't need anything about moments. But you do have a normalizing constant, a normalizing sequence, sorry, which is strong enough in order to kill the growth, the eventual growth of this summation. Okay, so you still have the almost sure convergence in this situation, and it is relatively recent, this result, and well, it uses it. It uses truncation in a rather different way, and together with a few tools that I will be mentioning a little bit later on in order to control this kind of probabilities, which is the main term, so what I will be calling the Borel-Cantelli summations. Now, one thing which is relevant over here, which I mentioned just briefly, is that many of these proofs are based on the Kronecker lemmas, which is something from number theory, where you just prove that this thing here, if you have this convergence, then you'll have this going to 0. Well, these small x's are just any real numbers, so you just use this in order to get this kind of convergence to 0. So instead of looking at this directly, you just prove that this thing here is almost surely convergent. This will be relevant to mention because once we replace summation, this summation here by a weighted summation, so you need to introduce weights on your summation, then you lose this tool, and then you need to have the control in a different way. Well, notice that here you can look at the normalizing constants similar to what is mentioned in Marcinkiewicz-Zygmunt, but then you'll have a result for p strictly smaller than 1. So while the full result with Marcinkiewicz-Zygmunt allows p to go up to 2. Okay. Now, so this means that in order to prove almost sure results, so strong laws of large numbers, we basically are interested, or one of the main tools is get some control over this kind of summations, which I will be calling the Borel-Cantelli summations. And this is known in the literature as a complete convergence of the sequence. So most of, at least the early results, would go, you prove complete convergence using this notation, and then the almost sure convergence would follow. Now, this is, for instance, the basic, the essential idea that was behind this classical result, which became, well, quite popular in the literature in order to compare the convergence rates. Again, linking the existence of moments with the convergence of the Borel-Cantelli summations. Well, of course, now you are dealing with lots of parameters over here. So you have an extra term alpha, you have an alpha p. So before we just have the p, which represents the moments of the random variables that we assume to exist. Here there is an extra term, so you allow from some adjustments to go from the convergence rate of these Borel-Cantelli summations and the normalizing constants that you should introduce in order to get almost sure convergence. Of course, the classical result, the Marcinkiewicz-Zygmunt, comes out from here, just taking alpha p exactly equal to 1. But this will mean, when you put it together with this condition on alpha, that from Baumkat you just get the Marcinkiewicz-Zygmunt in a restricted case of just assuming p be between 1 and 2. So you don't have the full result. And of course, just to remind you, here in this more recent result, we would have the Marcinkiewicz-Zygmunt, but now with p smaller than 1. So different methods give you partial results with respect to Marcinkiewicz-Zygmunt. Now, one result which is more recent and links to other approaches and other types of conditions that have been appearing in the literature is that in 2005, Lee and Spataro proved that if you have the existence of this moment, so there are lots of parameters here, I will not be commenting much about the choice of the parameters, sorry. But if you have the existence of this moment, this is equivalent to the convergence of this integral over here. Now, notice that now we are moving from the Borel-Cantelli summation, but now we need to get integration of the Borel-Cantelli summation. Now, these also prove that if you have appropriate moments, this is equivalent to this kind of results. Now, we all know that integrating tails is linked with expected values. So a few years later, these authors prove that this integral condition over here on the Borel-Cantelli summation is in fact equivalent to the convergence of these expected values, and where now you just truncate your random, your quotients with 0. So just keep the non-negative part, and you compute the mathematical expectation of this. Now, this is proved by Chen and Wang in 2008, and now this, the observation that you do have equivalence between this and then, of course, with the existence of these moments, which again links you with the Marcinkiewicz-Zygmunt, meant that people would be interested on replacing the Borel-Cantelli summations, so these kind of summations that you integrate over here, by directly these ones over there. Basically, when you try to prove that some condition is fulfilled, well, it is usually easier to handle the control of expected values than the control of the convergence rate of tails that you still have to integrate. So lots of people became interested on this kind of control, and so we introduced what people started to call in the literature the complete moment convergence. So you just replace the classical Borel-Cantelli by moments, well, appropriately chosen. And from here, you know that these still imply the almost sure convergence. By the way, I have here one small comment about the P and the QR. So I'm assuming that P is different from the product QR. If they coincide, well, you can still have a result, but instead of this moment here, you just need to go a little bit further on the moment that you need to assume to exist. Well, there are a few technicalities, which of course I will not be commenting, but in this, basically what is meant over here is that when you try to normalize by this term over here, you need to go a little bit further on the moment that one assumes to exist. So in the case they coincide, these two terms coincide, you just need to add a log term in order to get full control. Now, this is complete moment convergence. Well, this should be complete moment convergence and not moment complete convergence. It's interesting because together with these two inequalities, you can go from the complete moment convergence both to LP convergence and both to and also to almost sure convergence. So this means that in more recent years, people got interested on getting control over this kind of expectations. Okay, so this means that you start with actually with a smaller set of possible random variables because these imply a larger class, and you are trying to identify something that actually happens on a broader term. Now, this is way far behind, so this is a result from 1988, so long before one had noticed that you could use the complete moment convergence. There is an interesting result from Chow, which proved that if you assume this kind of, well, that should be smaller than infinity, so the existence of this expected value over here, then you will have the convergence of this term. So, for some reason, in 1988, Chow was interested on looking at these, the convergence of these expected values. Although by that time, no one had yet the information that this would be strictly useful to get almost sure convergent, but still probably was in the back of the mind of people back in the 80s. Now, let us have a quick look into weighted sums. So now I introduce a double indexed weights multiplying the x's. So this means that, as I mentioned before, the Kronecker lemma just is no longer applied. So you need a different set of tools in order to get the control of your summation. Now, the first result that appears available in the literature for weighted sums goes back to the 60s, where you have, well, an L2 convergence about the summation. So for each n fixed, you have everything should be normalized, but then you have an almost sure convergence. But notice that the normalizing sequence now it's weaker than what we should expect. Well, of course, one tried to extend this, and even Chow proved that you can replace the n to the power, the square root of n by n to the power 1 over p, if you assume the appropriate existence of moments. But notice that now we are restricting ourselves to p larger or equal than 2. Okay, but this, as we will see later on, is linked to the control of these kind of summations, where now here we have the weights are squared, but well, there will be a connection between the weights that we have here and this square that we see appearing here in the normalizing sequence. Now, I should mention that a few later on, even this this uniform control on the weights was proven to not be strictly necessary, and so you can have this convergence over here, well, with this assumption on the weights, just from the existence of sufficiently large moments of the random variables, which are still supposed to be ideal. Okay? Now, for a more general approach to results on convergence of weighted sums, you have one of which became probably one of the basic results on weighted sums, which is the Cousich result, which proved that if you now have this assumption, this control over the weight, so you replace here you have a square, now you have some other power, then if you have the appropriate moments, and the link between the power on the weights and the moments is expressed by this very usual relationship, if you remember a little bit of functional analysis, then you still have the almost sure convergence of the weighted sequence. Well, now with a normalizing, notice that here you have n to the power 1 over p, while here you have 1 over n. So you have different normalizations, but then you have a different link between the behavior of the weights and the moments that should be existing. Now, the proofs are all based on truncating arguments, so you just truncate your random variables appropriately, and then you try to use to get convenient control over the Borel-Cantelli summations that appear, and of course some control over the types. Now, one quick comment about this assumption on the weights. Cousich proved an example where he basically describes that the assumption on the weights is relatively sharp, because if you take q equal to 1 and you get this kind of choice for your weights, then this probability is 1, which means that you will not have almost sure convergence to 0. So somehow the assumptions that one puts on the weights is sharp in this sense. So if you relax the behavior of your weights, then you can lose indeed the convergence. Now, well, Cousich used himself with a few extra extensions on the normalization sequences. Well, again, you just introduce something which is complicated because, well, you just introduce the normalization should grow fast enough. You interpolate, well, you introduce a function, you start from here, so you define b on n, then you interpolate between consecutive points, and then you have a moment condition that you need to assume definiteness in order to get the almost sure convergence. Well, I just mentioned this just to see that you can actually go for a more general. I'm losing something on the microphone, so keep it here. So you can go for more exotic normalization sequences in order to still get almost sure convergence. Now, a few extra variances. If you go for the classical choices of the normalizing sequences, you can just prove that this thing here is equivalent to the existence of this moment. And if you have them bounded, you still just need this one here, which looks a lot more like the assumption that is used for Marcinkiewicz-Zygmunt strong laws. Okay. Well, few older results had proven that you can relax in some different ways the assumptions on the variance, but again, I will not be commenting that much about this. Now, older counterexamples show that some of the assumptions that you have on the normalizing sequence cannot be dropped. And Cousich also showed that if the normalizing sequence is growing at a slower rate than n, you will always find some distribution for which you will not have the strong law of large numbers. So actually, this increasingness assumption over here seems unavoidable in order to get an appropriate result. Now, Bai and Cheng wrote basically the same result as Kuzik mentioned, but in a different and a little bit more convenient way, linking the normalizing sequence rate with the existence of moments. Now, they proved that if your weights fulfill this assumption over here, then the parameters that you should use in order to get almost sure convergence are linked through this equation over here. So instead of having a summation that goes to 1, now you have 1 over p, though this is the normalizing sequence, is linked with the behavior of the weights and the moments that do exist in this way expressed over there. But they proved even more that if you have the converse implication over here for all sequences of weights satisfying this assumption, well, this is indeed an equivalence between the moments and the order of the convergence rate over here. Now, the tools becomes a little bit more involved because, well, as expected, you use truncation. Well, there is other inequality in order to try to separate weights from random variables and trying to control things. Now, this, of course, will appear because you will need to control some Borel-Cantelli lemmas, but the new tool that appears in this framework that allows you to get your final full control is that you have to rely on Bernstein inequalities in order to control the tail behaviors of the summations of your random variables. I just mentioned quickly that instead of normalizations of this sort, Bai and Cheng also consider normalization of this sort over here, where you have an extra logarithmic factor, but then results tend to start looking a little bit too technical, but the basic proofs, you can get results of this kind of normalizations with basically the same tools, with, of course, different technicalities in between, but you're basically the same idea. Now, some mention two random coefficients. So far, the ANIs are just real numbers, but you can get results equivalent to the ones that I have been mentioning. Well, actually, it is Kuzic, which again proved it almost everything in 1995. You can assume that your weights are random variables, and again, assuming that everything is IID. If you have the appropriate moments, then you'll have this kind of, well, now I'm not assuming that the mean is 0, but otherwise you would have a 0 here as your almost sure limit. So you can even get control on this if you have appropriate moments, assuming here. Notice that here Q should be larger or equal than 2, so the weights cannot be too random, so to say. Okay. Now, more recently, you have a partial extension on this, because now you are looking at between 1 and 2. And, well, with the different normalization of this summation, so meaning that you are getting some information about the convergence rate of your strong law of large numbers, so you can relax a little bit the existence of these moments, so you just need, well, relax. It is the other way around. You should have them not just finite, but defining summations which do not grow too quickly. But then instead of the moment of order p, you need to go to a moment of order 2p in order to get this convergence rate over here. So again, most of these proofs rely on truncation and convenient control on the Borel-Cantelli summations, plus some control on the tails. Most of them relying on the Bernstein inequalities that I have been mentioning. Well, actually, on this paper, they even prove that independence is really not necessary. You can have a relaxed way of dependence allowing. Now, the proof. I mentioned Borel-Cantelli, I mentioned Bernstein inequality, but this is wrong. Actually, there is a new kind of inequalities that is appearing, and the new set of inequalities that helps getting this kind of result is replacing the Bernstein, which I was wrongly mentioning, by some stronger inequalities, which are known as the Rosenthal inequalities, but they require that you have moments of order at least 2. Okay? So you have this kind of upper bounds, which prove that or show themselves to be the appropriate tool in order to get the control of the terms that allow you to get this summation. Well, I mentioned here Rosenthal inequalities because there is you can also insert a max over here, and they are basically proven to be more or less equivalent. Now, of course, as you expect, independent random variables satisfy Rosenthal inequalities, and there are a few other families of the dependent structures that will also be satisfying Rosenthal inequalities. So, in a sense, satisfying the Rosenthal inequalities has more recently become a sort of starting point in order to get asymptotic results of this sort. So, this is where I move from independence to dependence, and I just recall that most of the control over Borel-Cantel summations and the control of what is happening on the tails is meant to stabilize variance of partial sums. Okay. Now, the first set of conditions that were popular to control dependence were the so-called mixing conditions, for which I just recall here the definition of the strong mixing coefficients. Of course, as you surely know, there are lots of other mixing coefficients, but although the alpha coefficients being called the strong mixing coefficients, that are actually the weaker ones. Well, you just look at these probabilities, so you're just comparing what is happening with what would be happening if you do have independence where random variables are far apart, and you require these coefficients to go to 0. Well, usually this is not enough. You have these coefficients to go to 0 fast enough, but once you get the full control, you get the results. Okay, these were popular in the 70s and the 80s until people got interested on a notion that actually had appeared a little bit earlier, which are what I call here, which is known in the literature as generally as positive dependence. Well, there are a few variants of these. I just mentioned the ones that I found most significant. So I call it PQD, and PQD stands for pairwise quadrant dependence. If you have these kind of inequalities, so you have pairwise joint distributions compared with what you would have with independence. So this was introduced by Lehmann in '66 with a few other variants which I will not be mentioning. And on '67, these authors introduced the notion of association or positive association, where you just require that every covariance with f and g conveniently behaved are non-negative. Now, these became popular, say, in the early 90s. And at some point, before they became popular, these authors introduced what is called negative dependence, which just are constructed just reversing the inequalities that you have over here. Of course, for the covariances, you had to be a little bit more careful because the indices should not coincide and so on. But the idea is the same. Now, positive dependence was relatively popular in the in the 90s and the first 10 years of this century, and more recently people got more interested on negative dependence. I should say that I'm a little bit suspicious of negative dependence because of this, but as I mentioned before, much of the argument for proving almost sure results relies on having some control on the variance of partial summations, which of course you know can be written in this way. Now, if you have positive dependence, these terms are positive. So it becomes more difficult to stabilize these variances over here. While if you have negative dependence, well, these are negative, so the variance of the summation of the partial sum is smaller than what you would find in the independent case, so it should be easier to get a stabilization of the variance of the partial sums. Nevertheless, in recent years, concepts of negative dependence have become quite popular, but to my point of view, they are proposing assumptions which lack some kind of comparison of what is happening with respect to independence, because, as I mentioned here, the negative dependence case should be easier to control than what you find in independence. Of course, authors who are who deal with negative dependence will probably not agree with my point of view, but still, the idea is that negative dependence should be easier to control than what you have in the independent case. Now, some results of the same sort for positively dependent random variables. So the first result that appeared was back in the 1980s, where for centered random variables, not necessarily independently identically distributed, you can have almost the strong law of large number under this assumption over here. Now, this is a relatively strong assumption because you are comparing the covariance of this summation here with the final random variable that you get in this summation. So these terms are relatively large. So basically, this covariance should behave at least as order n. You should count about n terms over here. So the covariances should be decreasing relatively fast in order to keep the convergence of this summation. Okay. Now this is related with the Ethemadi's strong law of large numbers, where, if you still remember, a strong law of large number was proven assuming that you have negative covariances. So this is, and here we are assuming that covariances are positive. Now, well, this is for PQD. Well, PQD implied positive association. So if you just replace PQD by positive association, so basically you are just reinforcing the assumption over the moments, then you can drop this assumption here on the control of the first order moment. So you still have, well, the significant thing here is that the covariances should decrease at a reasonable pace. Otherwise, you lose the convergence over here. Now, again, proofs, you see the Borel-Cantelli summations coming up, and one more argument is that you should be able to control the expected values of these of the maximum of these summations over here. So what is usually known as in the literature as maximal inequalities, where you should have some kind of upper bound of this sort. Again, from the independent case, this is fine, but for dependent random variables and in particular for the associated ones, it is not that easy to get an appropriate control over these coefficients. Now, a few words on how to control these kind of asymptotic results for dependent random variables. So Cox and Grimet introduced these coefficients where you have pairwise convergence. Oh, by the way, notice that I have here these deltas defined with less or equal inequalities, but it is easy to check that you can replace the less or equal by reversing the sense of the inequality. It's just a simple algebra. And well, the interesting thing linking these coefficients with the covariance is that back in the 40s, Hufting proved that the covariances can be computed by double integration with respect to this function over here. So you have the sign of these terms controls the signs of the covariances. Now, Cox and Grimet introduced these kind of coefficients. These are relatively simple to interpret because if you think of the covariance as an infinite matrix, you are just looking at the covariance matrix dropping a strip along the diagonal. So the coefficient n taking summations over here, where we just drop what should probably be the most significant terms on the covariances, because well, the general idea on covariance is that if you look at indices which are far apart, the covariances should not be too large. Okay? So these became popular. And then you can use these coefficients if you have convergence. This is the kind of convergence that you get, or the assumption that you need on the Cox-Gribet coefficients in order to get maximal inequalities that allow you to get the proofs working on. So of course I will not be going into the details, otherwise you would not be following. But the general idea is that you have upper bound which have n terms in the independent case. So if you go to the dependent case, you expect to have n squared terms on this expected value over here. And so this kind of assumptions allows you to get an upper bound which is of order n again. So once you get an upper bound for these expected values over here of order n, you can expect to reproduce the arguments that allow you to conclude the proof in the independent case. So this is basically the general idea. Well, you can prove higher order maximal inequalities, and if you still remember correctly, this would probably remind you of a variant of what I called a few moments ago the Rosenthal inequality. So this is just a kind of variant of that. Now, well, you can get now other normalizations if you have an appropriate behavior on the normalizing constants, which, well, let me just go a little bit quicker over here. But this includes the case of normalizing sequence of n to the power 1 over p, but you need to get the control of this kind of term. This became relatively popular on the literature. It's about the best that you can get, but notice that the random variables here now look at the maximum of absolute values of summations, so things start to look a little bit more involved and a little bit more difficult to control. Now, a little bit easier to check in applications is the assumption which was produced by Louis Xi, where you, instead of looking at full covariances, will look at what is known in the literature as truncated covariances. If you remember a thing formula, when you integrate the delta jk over the whole plane, you will get the full covariances. Now here I'm just integrating over this square, so this is why we call this truncated covariances. Now, of course, if you put small v equal to plus infinity, you get the full covariances. Now, you need to have a convenient control on the growth rate of these kind of functions. And now, Louis Xi proved that under a stochastically domination convergence, so you don't need the random variables to be identically distributed, you just need to have some control, some uniform control over their distributions, and then you need this kind of assumption here in order to control the growth rate of the truncated covariances. If you have this, notice that while you are integrating something which 1 over so v to the power minus 3, which allows for some growth on the covariances, which should be careful tuned because, well, you integrate from j to the power 1 over p, and then you have this kind of complicated summation over here in order to get full control, and then you can prove this. Well, of course, I have not written over here, but if you have this almost sure convergence, you also have the strong law of large number in the Marcinkiewicz-Zygmunt version with the normalization 1 over p, because this one here is stronger than what you find in that case. Just to get some comparison, though this is what was proved by Louis Xi in 2019, you still have some extension of these results, but now instead of looking at this summation over here, you look at something where you integrate directly the delta j case, but then you no longer look at the square, you look at something which is a little bit more complicated, and the normalization comes outside, so it is somewhat stronger in order to get the same, well, and you don't have a result as strong as the Lewis version that you would have. But if you are only interested on the strong law of large numbers, you're probably more interested on this conclusion and not that one, which is stronger. Now, just a quick mention, because this author is also Portuguese as I am, my colleagues prove that you can even have a variation on this if you replace n by n1 over p, n to the power 1 over p, so looking like a Marcinkiewicz Zygmunt, but you'll need a logarithmic correction. But then I did not write it over here, I did not quote it, because, well, the assumption itself becomes a lot more technical, because you just do not integrate over a rectangle as you do here, but something which needs to be a little bit expanded before. Now, these authors that I mentioned before, again, with this kind of control over the Cox-Grimet coefficients. And by the way, I did not mention at the first time, but notice that this is not a very strong summation or a very strong condition, because you are just making a summation on points which go as 2 to the power n. So you are removing at each step a very large strip of the covariance matrix. So basically you are moving away from what should be expected to be the most significant